Hello, Professor Jinsi Yang. Good evening, and thank you so much for considering to talk with me for our Soft Computing Research Society Tech Magazine SCRS Insights. Professor Jinsi Yang, to begin with, please tell me about yourself, your academic background, your current affiliation, please.
Thank you, Professor Jagdish. It's really a pleasure to meet you, even it's online. Uh, I was trained as an applied mathematician with a PhD or DPhil from University of Oxford in applied mathematics. I also got a master in physics and computing. In the last 20 years or so, I have been working with engineers and computer scientists trying to solve various real-world problems. For example, we try to solve problems from the theoretical perspective, which is mainly modeling, but also we try to solve them from the practical perspective, we try to see whether we can optimize things, which is, again, we have a real problem. We try to optimize certain objective. Currently, I'm a reader in modeling and simulation and also optimization at Middlesex University. As you know, reader in the UK is equivalent to the maybe a professor, a full professor in the
Yes,
US academic system.
that's right. And do you have any previous experience of the job? Means earlier you have worked to some other university before?
Yeah, after graduate, I work in the Cambridge University, work with a lot of engineering project. Then after that, I went to the National Physics Laboratory in London, which is a very prestigious research lab in the scientific computing division. Many years ago, Alan Turing was in that division. So we
Wonderful.
were doing a lot of scientific computing. It's mainly simulation, yeah, and
Exciting.
statistics.
Actually, exciting background you have. And
Thank you.
I understand that I'm also a student of applied mathematics and then turned to the swarm intelligence. You also have the similar background and then turn to the swarm intelligence. I know you are one of the world's topmost swarm intelligence person. People have
You're very
studied
kind.
your papers, your books, and made themselves expert in the swarm intelligence. Still, just for the completeness, I want to understand from you, apart from the swarm intelligence, what are your research areas? What are your research interests? What kind of research you are doing? Particular kind of projects you are doing?
Yeah. The as I said, I'm trained as a mathematician. So my actually initial interest was mainly mathematical modeling. Try to use a partial differential equation or any mathematical tool to simulate the things and modeling things. Uh,
So,
in the
Professor,
last 20 years, I work with a lot of engineers. Then I realized a lot of problems in engineering actually are more interested, not just from the theoretical possibility, but also from the different way engineers solve problems. So I gradually move away from applied mathematics to algorithm and especially heuristic algorithm and optimization algorithm. Of course, recently I'm also interested in the AI and machine learning, but all these things are a spectrum of, in a way, using applied mathematics technique and the computing technique to solve problems.
that's a wonderful. Actually, what I also feel personally that all the machine learning or artificial intelligence based techniques are studied by or are dealt by a mathematics background person, then the dealing is different, and you can see from the AI algorithms from mathematics point of view. Then you can see sometime the hidden power of the AI also, and the research directions will open also. You mentioned that you particularly are particularly interested in the mathematical modeling, right? So I know that you are solving optimization problems using swarm intelligence based algorithm. Do you model the real world problems to some other kind of models also apart
That's
from the
true. That's
optimization?
true. Yeah, maybe I can give you two examples. During my PhD, I try to model the uh, porous media flow or the multi-phase flow, which means the oil, gas, or water filter through the soil. Then I built actually a very complex model. So
Hmm.
this is a kind of modeling which is not only useful from mathematical perspective, but also from the environmental science point of view, because you can say how to simulate the pollutant in the soil, in the water, how they gradually propagate through the soil. Then you have a way to predict how far they can travel. Then anyway, you can probably stop the pollution. So this is one type. The other type is I did in the one of the big project in the NPL. It's kind of simulate how to use hydrogen to generate electricity. It's a hydrogen fuel cell used in car. But of course, it was a very challenging problem because the reason is some of the film are so thin.
Hmm.
Even use say finite element method, the mesh can have to be very small. So it's a computation very challenging. Of course, I did many other
So,
type of modeling. Yeah.
so Professor Yag, both type of models that you prepared are partial differential equation, optimization. What kind of models you are making out of
The
these?
mathematical, that's a very good question. The mathematical side, we always tend to start with a partial differential equation because we start with, say, physical law like conservation energy, momentum, and then, of course, it depends on the actual area. We may need other law like the Darcy's flow law, and but this is just the mathematical model. But
Hmm.
of course, you when you put into the actual material quantity, we do need to see whether the kind of material property, whether how sensitive the results to this kind of material property. Then we do sensitivity analysis and optimization. So we tend to start with PTE.
PD. So,
Yeah.
when you model for these kind of very, very applied problems to in terms of the partial differential equations, do you have the ready-made partial mathematical methods, mathematical techniques so that
Uh,
these algorithms
that's true. Yeah, that's a very good question because most of these partial differentiation are not easy
not,
to solve.
yeah, that,
Most time we can only say try to approximate the equation by either say first non-dimensionalize or scale them in such a way it's easy to figure out the scale. Then we tend to see whether can solve it. Most time we cannot. But then we try to use approximation method. The two important methods I used a lot is one is a symptotic analysis, basically say how far in we can get in terms of the far field, short time and the long time behavior. The other time is perturbation. We basically say, let's see we can do like the Taylor expansion, first
hmm,
order approximation, then second order to see whether in the end we get some sense, but not all the information. Then we have to solve them numerically. It tends to be using finite difference at first, then sometimes finite volume or finite elements.
yeah, finite element methods you can use. So, but means the original partial original model of the problem is usually solved using the approximation methods. The
That's true.
approximate model is actually solved, not the original.
That's true. That's true.
So I think here is the one that's my interest also, that since you are approximating the model and then solving and then applying the numerical methods to solve that problem, do you think that your swarm intelligence based algorithms uh, can somehow handle the original model?
The short answer, I guess, it's not. The reason I move away from the mathematical modeling is I find that most of the problem are not easily solvable.
Yeah,
But then when I work with engineers and engineering project, we
right.
found that many of the problems are not that difficult from the mathematical sense, but they are also very interesting, but also difficult to solve. Even, for example, when you have a design problem like the building design or a lot of the engineering structure design, they may not have differential equations, but they have a non-linear objective like the weight and also the stress and the pressure, all this forcing or design regulation. But you can write them most time as a set of non-linear even algebra equation. But
Mhm.
when you try to actually solve them, it's not that easy because one is a higher dimension. They tend to have several hundred, even thousands of design variable.
Variables, yeah.
And also, these kind of expression are highly non-linear. So there's no easy way to see. Then that's why I gradually use optimization technique. But of course, as you know, there are a lot of old technique like say Newton-Raphson, which is very efficient, but they tend to depend on where you start. Then they also solve the problem one time one at a time. But then the swarm intelligence idea came in, basically saying, why not find the multiple solution simultaneously to see whether you can,
Yeah.
based on the different solution, to improve them. That's swarm intelligence come into, and also we find it's very, as you know, efficient in many of the problems.
Exactly. That's the problem with the traditional methods. Simultaneously, the Newton-Raphson method solves the problem one at a time, provide one solution at a time, and there are limitations that the function should be differentiable.
That's
Uh,
true. That's true.
the modeled problem should be differentiable, and sometime if you have a problem which is not differentiable, sometime even you cannot analyze the problem. In that case, you cannot guarantee that Newton-Raphson method can be applied or not, is
That's
even
true. Yeah.
applicable or not. So yes, there are challenges, and uh, uh, you know that the swarm and evolutionary algorithm can be applied to such kind of problems which otherwise cannot be solved. And if they can be modeled as an optimization problem, and if you do not have any particular kind of traditional mathematical methods, then of course the swarm and evolutionary algorithms performs better, and they come as a rescue to the optimizers. So
That's true. I
and
totally agree. Yeah.
as I mentioned initially also that you have proposed one of the most popular swarm intelligence based algorithm, Firefly algorithm, apart from the other algorithm like Cuckoo search, bat algorithm. Uh, you have invented so many algorithm, and they are very well cited, very popular algorithm, and they are I read so many papers of you, and these algorithms are being applied to so many real world problems, and people have successfully solved the problems. Do you want to say something more on Firefly algorithm, how it works, and
Yeah, it's an interesting start. Is actually maybe one of the reasons I watched a lot of BBC documentary, The Natural World, and
right?
also when I actually watched this TV program, and also when I was a small boy, I also we had a lot of actually firefly in the region I live. And also, I always fascinated by the flashing behavior. Then gradually, when I was trying to solve engineering problem, I was thinking maybe let's try to get any inspiration to see whether we can do something. So that's one of the reasons. The other reason is actually I tried quite a few methods, say Newton-Raphson and say Hooke-Jiva, and also the particle swarm optimization to solve the engineering optimization problem I was trying to solve, which they have a few hundred design variable. Uh, One of the reasons we use particle swarm at that time is they say it's a it was popular, and also it's easy to implement.
Yeah.
Then we found that the PSO, particle swarm optimization, it has some premature convergence. One of the reasons is it's the velocity. It's related to energy. It's half mv squared. It's the energy, kinetic energy. If the
Right.
energy is too high, then the system would becomes swarming around, become unstable in a way. It's difficult to cool down. So I was thinking maybe we should get rid of all the velocity. That's why, based on this swarm behavior of firefly, I was thinking maybe let's just say the two solution uh, can be encoded as the location of the two firefly.
Mhm.
When the firefly flash, they try to move around. Then we say to see the similarity of the two solution or the difference of the solution. Then in the end, that's why in a way it's the firefly algorithm seems works very well without using any velocity. But of course, many other researchers have done so many wonderful study use this algorithm, then they prove that it can solve a different type of problem, which is wonderful because that confirm initially our in a way the thinking, which means it may work. Yeah.
So, Professor Yang, actually, this your statement is very, very useful for the researchers who are into the swarm intelligence, who want to understand that how the researchers think that they are developing the new algorithm. So you said that there are certain lacuna. Premature convergence is the one very, very significant lacuna in particle swarm optimization. So you thought to develop a new algorithm which is inspired by the Firefly working. So, can any do you want to mention any particular thing, any particular idea, any particular component that you have added, which is actually tackling the premature convergence in Firefly? Means,
Oh, that's a very good question. Is uh, I think the main one of the two reason in PSO,
Mhm.
the reason it cause premature convergence, one is the energy too high. The other one is how you damping the system. That's why people introduce the later on the what called inertia factor or
Right.
weighting.
Hmm.
But from the Firefly system point of view, the inspiration is this. When I watch the television, they have the time lag photography. You can see there are two characteristics. One is the paths traced by firefly are very sparse, which means in a vast search area, we do not need to try every possible region. As long as the paths are sparse, they can cover a large region. That's one of the characteristics in the actual firefly system. The other thing is the flash, the light intensity will decrease with distance. That means the local brightness would be dominating compared to the long distance other firefly. This would give us inspiration saying when you calculate, say, suppose you have 10 different solution in a search space,
Mhm.
then some of the solutions are closer, they may have very strong similarity. If it's further away, they may not. So I added the exponential decay, which means we control basically say the solution short-term attraction in the firefly or local solution are more important when you're updating the solution than the long distance one.
So
But of course,
diversity,
we have to
diversity will
balance.
be,
That's true.
yeah, diversity will be maintained because of the low cost solutions, and you are not killing the low cost solutions. You are keeping them as well.
That's true.
Keep the energy live.
You're right. It's a really difficult challenge to balancing the local exploration and long distance exploration. So it's a bit of balance. But I think the Firefly works. The reason is we input that attractive as exponential decay, it automatically take care of this kind of balance, and also depends on the parameter gamma e to the gamma the
Right.
distance. Then there's of course in the minus signs it's an exponential decay. Then we can control how strong the local and the versus global. Uh, the amazing thing we found later on is after we code the I coded the firefly behavior in the MATLAB, then I found under some condition a large swarm can automatically subdivide into multiple swarm, a small swarm, which
Wow.
means this kind of behavior, which means it's not in a way we can see initially. But because of this attraction, then if it's multi-swarm, suppose you have a multimodal problem, each the swarm can swarm locally around.
Yeah.
So which
So
means
you mean,
Firefly can deal with a multimodal problem.
yeah, you
Yeah.
mean Firefly algorithm is actually inherently parallel.
Yeah, in a way, you're right. If it's a subdivided, there's a
Yeah.
potential possibility to parallel the large swarm into multi small swarms. Yeah.
So actually, thank you so much about this Firefly algorithm. This is one of the very famous algorithm that I studied during my initial days of swarm intelligence studies. And I'm really very fascinated. I studied your cuckoo search algorithm, BAT algorithm. Many congratulations for so many new algorithm and so much great contributions to the academics, sir. Uh, you know, after having so many swarm intelligence or evolutionary algorithms, I hope you are aware that I think more than 200 swarm or evolutionary algorithms are available right now.
I saw recently there's a paper they say 540 different
Wow, great.
albums. Yeah,
So
that's
500 plus,
really a lot. Yeah.
yeah, really lot. So after having 500 and plus so many different algorithms, do you really think that the new researchers should explore in designing the new algorithm in this area? Do you really think that is it good
That's a
idea?
good question. It's a really difficult to say because uh, in one way there are so many different algorithms, especially in the last 10 years. Probably
Right,
there's more than 80% of the more than 500 algorithm was developed in the last 10 years.
right, Jack.
Uh, the good thing is it people or researchers explore different way of potential problem solving, but also there's a not so difficult good ways. Many of the algorithms are very similar. It's in a way it's not maybe the name could be different, but many of the search mechanisms are not significantly different. So I would think is for the new researchers, they should, if they can find any new search mechanism, yeah, why not design new algorithm? But if they only use old search mechanism, then there's no need to call something new.
Mm.
So it's something really a new way to search things, then a new way of problem solving that should be encouraged.
So, Professor Young, if I understood correctly, I also feel the same way that most of the time the researchers are naming it differently. The background concept is the same, and by and large, they are using ultimately the Euclidean distance-based update mechanism, and they are just changing some coefficients, and most importantly, they are just changing the inspiration. And this is not a good idea in particularly. I think it's not good idea to deteriorate the subject area like this, that you are presenting the same thing with a new cover. So the researchers should also be aware of this, that it should not be done.
That's true. Yeah.
But I think as the problems every day, the new problems are coming. So there may be a requirement for the new algorithms, but it should be really new. It should not be the just a different cover with a different cover, the same algorithm. So in the field of swarm and evolutionary algorithm, uh, apart from the proposal of the new algorithm, what kind of research directions you want to suggest for the new
Oh,
research?
that's a very good question. Is as one of the question, as you know, we discussed before between
Mhm.
you and me. Is it's the benchmarking because a lot of the published paper and a lot of the publication,
Mhm.
people use smooth functions to test new algorithm and a new method. But this kind of smooth function, there's nothing wrong, but they are not really related to real world application. It's kind of a specialized smooth subset of a function.
Yeah.
Uh, it's useful, but not that useful. But a lot of the researchers focus too much on this. We would suggest that we should use a real world case study as benchmark to actually validate the new algorithm or new technique. Uh, so as you say, we should maybe, as you many years ago, you also started to build a website. Maybe we should build some a set of a public domain case study so that people can use with code then to benchmark the new technique. So
Sure,
this is the
sure.
one thing. Yeah,
And I remember we started this long
yeah,
back. We thought to start this project, but somehow it could not be implemented.
yeah.
We'll
We'll
think.
keep that ongoing.
Yeah,
Yeah.
hope to work on that. Yeah.
Yeah.
Any
The other problem is the mathematical framework. As you say, your background and my background are applied mathematics. It would be wonderful to see how different algorithms works. At the moment, engineer and many publication, especially the applied research, you just say, I use this algorithm, I try to tune the parameter, then I go to the good results. But the question is, how do we predict how good the algorithm would perform under certain parameter setting and what condition? How we understand we know they works most time, but not 100%. But we really understand why they work under what condition. So from mathematical point of view, this would be a good research. Would be say, can we build something mathematical theory to analyze such algorithm like the convergence, rate of convergence? So
Yes.
this would be another area, a
So
good area.
now, till now, you have mentioned two very, very important research ideas for the young researchers, and I think, for every idea, people can do the PhDs. So, one
That's
is
true.
the
That's true.
benchmarking, another is the mathematical analysis. Any other?
The other would be, I think one is maybe I have two other. One is the parameter tuning. A lot of things we tune parameters. Uh, then what? How do we set the parameter? I think the most easy way is just say I use the parameter published, then I as the base. Then I try to vary the parameter slightly to do a little bit of parametric study to see whether this tune the algorithm better.
Yeah.
But I would think we should have a set of a method to fine tune all the algorithm or any of the algorithm given with a more efficient way to tune this. But at the moment, there are more than 10 different tuning methods, like a Monte Carlo, but there's no systematic way to say this type of algorithm tuning method would be better. That's one thing. The other thing is, uh, as we mentioned quite a few times, swarm intelligence. The definition is it's we know what they mean, but the definition is not rigorous. We suppose we give a set of multi-agent or swarm, a swarm. Can we predict the swarm behavior? Basically, say what do we mean by swarm intelligence? Is there any Are there any condition we can figure out to say under this condition the swarm will behave something more intelligently? And if these conditions are not satisfied, they may not have any intelligent behavior. So it's kind of in a way it's the rise of swarm intelligence. It's some a kind of theory or maybe observation or some condition we can figure out. Of course, in physics, we know how they say transition, phase transition from say water to ice, then from say water to snowflake. But they are very regular structure. I always think the swarm intelligence is like a self-organized system. Basically, initially you initialize like a Monte Carlo a set of a random location, then gradually converge into a regular structure. One of the converged structure would be ideally in the region of optimal solution.
Yeah.
That we will make sure we find the optimal solution. But how these things uh, actually converge to an organized structure.
Mhm.
Physics, they have some theory, but so many have nothing, have no
So,
theory yet. Yeah,
for Swamit, I have actually immediate two queries or two
yeah,
interests Uh, for having the swarm intelligence, of course, the one very important idea is the minimum swarm size. What should be the swarm size? So there is a paper, there is a research done by Maurice Clark. I think in his book he mentioned that minimum 12 should be the swarm size, so that it will be an intelligent swarm. Another
Okay.
Another is the necessary and sufficient condition for the swarm intelligence are the two conditions, that self-organization that you already mentioned, and the division of labor,
Yeah.
the assignment of work, distribution of the work among the different entities. So if these, what I studied about the swarm intelligence, that if these two conditions with certain number of individuals in the swarm, if these two conditions are satisfied, self-organization and division of labor, then we can expect the swarm intelligence. But I
That's interesting. Yeah.
Yeah, but as you mentioned, this the mathematical validity of having the swarm intelligence is the one very important challenge, because you can expect the swarm intelligence, but there is no guarantee that the solution is intelligent solution. So
That's true. That's
mathematical,
true. I totally agree with you. Yeah.
so
And also in terms of the population size, I'm not sure whether 12 or what's the actual number. I remember in the microgenetic algorithm, they
Mhm.
say at least you need three. The population should be three. One is the best solution, the other two
Are
would
the
be
certain.
perturbation. Then they have the population size of five as a micro J. But as you said, there must be a minimum. If it's one, there's no more swarm. So there must be a small number of agent. But how small? You're right. We might have say a mathematical indication in some range, but there's no guarantee certain behavior will emerge in such a small swarm.
Exactly. So, experimentally, we can expect that, okay, the solution is coming out to be intelligent, swarm intelligence behavior is emerging, but there is no proof that yes, it will always be there. And
That's
if
true. That's true.
if the guarantee is not there, then for implementation to the real world problem, we cannot expect the correctness of the solution.
That's
So
true. That's true.
yeah, so this is very important idea that mathematical studies can be done for the swarm size also, for the definition of the swarm intelligence, for the conditions of the swarm intelligence. You mentioned about the parameter tuning, right, Professor?
Yeah.
Yeah, I'm just wondering, actually, is there any possibility in the field of swarm and evolutionary algorithm to have an algorithm with parameter free?
Uh, it is possible. This is a good question in a way. If we do not have suppose an algorithm without any parameter,
Mhm.
it's there's no need to tune, but it also limits the versatility or flexibility of the algorithm because with the parameter, you may able to tune the algorithm to suit a different possible problem. If there's no parameter, basically it's that tool is stuck. Whether it's good, then it's good. If it's not good, then you have no way to tune it.
Mhm.
So so it's like the many of the tool. If the two general purpose one, like the Swiss Army knife set, you need to. They have a multiple tool. They can do a lot of things. But if it's a no, say, tuning like the Chinese chopstick, just then you have no way. But you have to use that skillfully. Then you can solve problem. So it's a balance between general purpose and the specialized tools.
Yeah, but in general, parameter-free swarm and evolutionary algorithm is relatively difficult, right?
That's true. But I would think the adaptive algorithm would be better. Basically saying we have some parameter,
Mhm.
we should change the parameter, change the value according to the solution quality. Then
Oh,
we
adaptive.
it's a kind of adaptive swarm
Got it.
intelligence would be a
Wonderful.
better approach, I would think.
Wonderful. Now understood. Understood. So it means it's not completely parameter-free, but the parameters are adaptive, and
Yeah,
users need not to fix the parameters.
that's true. Yeah.
According to the problem, the algorithm will itself set the parameters.
That would be ideal. So you're right. So either you vary the parameter according to certain rule, or the rule can be learned from the problem, like the machine learning technique plug into the swarm intelligence. They learn from the history or data to see whether they can increase a parameter or decrease it or even stay the same.
Right.
So that would be one of the thing to explore. The other thing, of course, many people try to do that. For example, the differential evolution, they have the adaptive one, basically to say, if the solution we run 10, say, iteration without improving, we change the value of that parameter. If
Scale
it's
parameter.
continually improving, we stick we do not change that parameter for the moment. I think the other area I would think would be the quantum computing. Basically, to say we use nowadays quantum computers started to emerge,
Right.
but also very expensive. But we have a lot of quantum simulator. It would be good to explore the swarm intelligence in the quantum environment to see whether we can make things better.
Yeah. So I found this is another area of research for the young researchers, the implementation of swarm and evolutionary algorithm in the quantum environment.
Yeah,
Yeah.
that's true. It's quantify the the swarm intelligence to see whether we can improve the performance.
Yeah, that's right. Thank you, Professor Yang. This is a great discussion, and actually, I'm personally very happy to have this kind of discussion where we think, we discuss, we think on the possibilities in the area, in the improvement in this research area. We have discussed a lot. We have given a guideline during this discussion to the new upcoming researchers. They can work on the benchmarking, they can work on the mathematical analysis of the algorithms, they can work on the parameter tuning, of course can think of the adaptive parameter setting also. They can think of the mathematical conditions to have to guarantee the swarm intelligence also. And the last that you suggested, the implementation of swarm evolutionary algorithm to the quantum environment. Wonderful discussion. Thanks a lot. Excellent. Please
Thank you very much. You're welcome.
keep
Yeah.
in touch. And here I will stop. Again, I'm thankful to all this discussion to guide the young researchers. Thank you so much, Professor.
Thank you. You're welcome. Thank you.
Thank you. Bye. Bye.
Bye.
Uh, I'm